Year 13 Vectors, Lesson 2. We're going to have a look at a number of problems involving vectors, some relating to mechanics. Let's have a look at the first example. So, the map of a large area of open land is marked in 1 kilometre squares, and a point near the middle of the area is defined to be the origin. The vectors 1, 0, which of course is the I vector, and 0, 1, the j vector, are in the directions east and north. So this is simply clarifying that the I vector is in this direction and the j vector is in this direction here. At time t hours, the position vectors of two hikers, Ashok and Kumar, are given by these vectors here. So the position vector, remember it's a position relative to this origin, is dependent on the time. So, part 1, we have to prove that the two hikers meet and give the coordinates of the point where this happens. So, if the two hikers meet, there must exist a time t at which they have the same position, i.e. there must exist a t such that RA is equal to RK. Remember, when you're answering questions and you're referring to vectors, you need to underline your vectors in the question. Of course, they'll be in bold. So this means that we can say negative 2, 0 plus 8, 1t is equal to 7t, 10 minus 4t. Now, the vector RA, we can combine it like the vector RK as follows. So negative 2 plus 8t, and then t for the j component. And that way it's a little bit easier to compare the two vectors. So let's have a look at the I direction and what that tells us. So these components here. Remember, if two vectors are equal, then their I components must be equal and their j components must be equal. So comparing the I components tells us that negative 2 plus 8t is equal to 7t. This gives us that t is equal to 2 hours. Now, let's see what happens if we now equate the j components here. We'll get another equation, t equals 10 minus 4t, and if this equation has the same answer for t, then the two are consistent and the two hikers can be at the same position at this time. So, of course, rearranging this gives us 5t equals 10, t equals 2 hours also. So we have proven that the two hikers meet when the time t equals 2 hours, and the coordinates of the point where this happens, we can substitute t back into either one of the position vector formulae. So t equals 2 gives us the position of both hikers as 14, 2. As a vector. The question does ask us for coordinates. Don't get coordinates and vectors mixed up. It's asking for coordinates, so we need to give the answer as 14, 2. Part 2. Compare the speeds of the two hikers. So we need to remember that speed can be calculated by differentiating our position vector here with respect to time, which means we need to differentiate the I component and the j component with respect to t. So vector RA will differentiate to give me vector VA. I'm going to use this version of the vector, it's a little bit easier to see there. So differentiating that gives me 8, 1. So that would suggest that Ashok is travelling with a constant velocity. What about VK? Let's differentiate the other vector. So that gives me 7, negative 4. Again, constant velocity. Neither of these velocities are dependent on time. The question does get us to compare the speeds of the two hikers. So remember, speed is the magnitude of the velocity vector. So we need to work out the magnitude of each of these vectors. So that comes to root 65 kilometres per hour for Ashok. And then for Kumar, that would be 7 squared plus negative 4 or 4 squared, which comes to a value of route 65 as well. So comparing the two speeds of the hikers are travelling at the same speed. They have different velocity vectors, which means the directions in which they're moving are different, but they are travelling at the same speed, and at 2 hours they end up in the same position. Example 2. Two beetles, A and B, are on a large patio which is modelled as a flat horizontal surface. Cartesian axes are defined relative to an origin near the middle of the patio. The direction of the x-axis is east and the direction of the y-axis is north. Always read through this information and check that it makes sense. So the x-axis is in its usual position, the y-axis also in its usual position. And the unit vectors 1, 0, which is of course I, and 0, 1, which is j, are in the x and y directions respectively. The unit for distance is 1 metre, time is measured in seconds, and time is between 0 and 5 seconds. We're now given the position vector, RA, of beetle A, which is here. So we've got a number of questions to work through. We're going to move through to the next page where we've got some more space in which to do the working. The question will appear again, it will be much smaller. You have the matching PDF with the question on it from which you can do your work. So let's have a look at part 1 of the question. Write down beetle A's velocity and acceleration at time t. So we know that we can find the velocity vector if we differentiate this position vector here with respect to time, which means we need to differentiate the I component, which gives us 1, and the j component, which gives us t2. So I'm differentiating here. So that is my velocity, or beetle A's velocity. Now the acceleration of beetle A is the derivative of the velocity vector with respect to time, which gives me 0, 2. So beetle A is travelling with a constant acceleration. Let's read the next piece of information. Beetle B is initially at the point -1, 10, moving with velocity 1, -4, and also has a constant acceleration 0, 2 metres per second squared. So part 2, find the velocity and position vector of beetle B at time t. There are different ways in which you can do this. Because beetle B is travelling with a constant acceleration, we can make use of the Suvat equations in vector form, or we can integrate the acceleration vector to find the velocity vector. We can then integrate the velocity vector to find our displacement vector, etc. I think it's going to be a little bit simpler to make use of the Suvat equations in their vector form. So let's write down what we know. So we know that initially we have a displacement of -1, 10. We know our initial velocity is 1, -4. We don't know what v is, so that's a question mark. We do know acceleration is 0, 2. And we're actually asked to find the velocity and position vector at time t. So to find the velocity, I'm going to make use of v equals u plus at. So that is 1, -4 plus my acceleration vector 0, 2 multiplied by t. So how does this simplify? This simplifies to 1 and then 2t subtract 4. So this is the velocity of beetle B. Just write a little b there so we know it's beetle B. Now, position vector. So I'm going to make use of the Suvat equation. S equals ut plus a half at squared plus s0. The plus s0 accounts for the fact that this beetle did not start at the origin. So let's substitute in everything. 1, -4t plus a half, 0, 2 t squared plus -1, 10. Now, if we want to, we can then simplify everything as one single vector, identifying all the I components. So that's t minus 1. And then for the j component, negative 4t plus t squared plus 10. And we have our position vector in terms of t. So remember, it was the position vector, which means we must work out the vector relative to the origin, not just the displacement. If we had not included this part here, then all we would have is the displacement from the starting position of negative 110. We want the position vector, which has to be relative to the origin. So we have to add on the initial movement. It's a little bit like this. Imagine here is our origin. Beetle B starts off here, which is the point negative 110. It travels to some other point here. Let's just mark that in red for clarity. If we just applied s equals ut plus a half at squared, we just end up with this blue result here. So that accounts for this part here. But the question, keep coming back to it, says find the position vector of Beetle B. Well, the position vector means we need this vector here, which means we have to add on this vector here, which is this part there. So the red and the blue vector combine to give us the green end result here. So remember, we could have done this with integration as well. If you are going to do that, don't forget that any constants you include must be in vector form when you're integrating vectors. So part 3, let's move on to that. Show that the two beetles meet once and give the coordinates of the place where this happens. So I'm just going to cordon off a little bit of space here so we can keep working on the same page and still see the question. So let's have a look at part 3. So if the beetles meet, they have to be at the same position. So we've identified here this is the position of Beetle B. So if they meet, we know that RA must equal RB. They must be at the same position at the same time. So let's equate RA and RB. So that's t minus 1 t squared minus 2 for RA, which has got to equal t minus 1 negative 4t plus t squared plus 10. Now look at the I components. It doesn't matter which value of t we're at, the I components of the positions of the two beetles are the same. So they always have the same x coordinate. Now, what about the j components? Let's equate those. So t squared minus 2 equals negative 4t plus t squared plus 10. This is actually going to turn out to be quite a simple equation. I think the t squareds will cancel and we are left with 4t equals 12. So t is equal to 3 seconds. So the two beetles meet after 3 seconds. Now to find out the position, we need to substitute into either RA or RB. RA is actually a slightly simpler formula, so I'll substitute back into the result for RA. So that gives me 2 and 7. Now it does ask for the coordinates. So let's make sure we provide a coordinate 2, 7. Right, the next part, part 4, show that the directions of travel of the two beetles are never parallel to each other. So, this is important. If you are asked about the direction of travel, which vector tells us the direction of travel? Think about it carefully. It's not the position vector just tells you where you are at a given time. It is the velocity vector that tells you about the direction of travel. So we need to be looking at the velocity vectors here. So what do we know? We know that VB is equal to 1, 2t minus 4. We worked it out earlier. VA, we have, it's 1, 2t, like that. Now think about what we learnt about parallel vectors. If VB and VA are parallel, that must mean that there exists some value k or m or whatever, let's say m, so we don't get ourselves confused with a k direction. So 1, 2t minus 4 must equal m multiplied by 1, 2t, i.e. the vectors must be multiples of each other, okay? So one vector is a multiple of the other, or the other way around. Now, what does this then tell us? Well, if we look at the I components here, they have got to be equal to each other. So this implies that 1 must equal m. Now, let's have a look at the j components here. What does that tell us? Well, they tell us that 2t minus 4 must equal m multiplied by 2t. But we've just worked out that m equals 1. So this tells me that 2t minus 4 equals 2t. And subtracting 2t from both sides gives me negative 4 equals 0, which we know is not feasible. So that is clearly not possible, which instantly tells me there is no solution, i.e. no value of t can make this true, which implies that the Beetles can never be travelling parallel to each other. It's a little bit like a proof by contradiction, which you may have come across. We assumed something was true, and we showed that if it were true, this would completely break down as an argument and become impossible, which means that the original assumption that we made had to be incorrect. Right, this takes us on to part 5. Prove that there is one, and only one, time at which the speeds of the two Beetles are the same, and find the speeds at this time. So, speed, that means we need to find the magnitude of each velocity vector. So let's remind ourselves the velocity vector b is equal to 1 and 2t minus 4, which means that the speed is the magnitude of this velocity vector, which is the square root of 1 squared plus brackets 2t minus 4 all squared. Beetle A, if we remember, has a velocity vector 1, 2t, which means if we work out its speed again in a similar way, that's 1 plus 2t all squared. Now, if the speeds of the two Beetles are the same, that tells us that mod VB must equal mod VA. So that tells us that these two results must be equal. Just expanding that bracket there. Now we can square both sides, which tells us that 1 plus 2t minus 4 all squared equals 1 plus 4t squared. Let's continue simplifying. So that's 1 plus 4t squared minus 16t. 16 is equal to 1 plus 4t squared. I can cancel 4t squared, cancel 4t squared, and I can cancel a 1 and a 1 as well, and I'm left with a very, very simple equation. 16t equals 16 and t equals 1 second. So there's clearly only one time at which the speeds of the two Beetles are the same. What is this speed equal to? Well, let's simply substitute into either one of the speed calculations, and we will find that we get an answer of root 5 meters per second. So example 3, we've got another quite extended question. So let's read through all the information really carefully. Don't ignore this information at the beginning, there could be useful content here. So positions are given relative to a fixed origin. The x direction is east and the y direction is north. So we're dealing with the usual situation regarding the axes. Two boats, the Rosemary and the Sage, are having a race between 2 points A and B. We're given the position vector of the Rosemary, and we're given some initial conditions. The Rosemary is at point A when t equals 0 and point B when t is equal to 2. So part 1, find the distance AB. So let's work out the position vectors of the rosemary at these 2 times. So let's say see what happens at time t equals 0. So we can work out RR, I suppose, the position vector of the rosemary as 3, 2 by substituting t equals 0 into here. Then what happens if t equals 2? We can see that if we substitute that in, we'll get 3, 2 plus 12, 16, which comes to 15, 18. So imagine what this looks like. The rosemary starts off at a point 3, 2 at time t equals 0, and it ends up at a point 15, 18. Remember, the position vectors give you the coordinates. So there's A and there's B, and we need to work out the distance A to B, which we can do very simply using Pythagoras Theorem. You can see your right angle triangle here has got a base of 12 and a height of 16. So the distance AB is simply equal to 12 squared plus 16 squared, all square rooted, which comes to 20. Kilometres. Part 2, show that the rosemary travels at a constant velocity. So we can find the velocity of the rosemary by differentiating this position vector up here. So we might want to actually write this position vector as one single vector like that, 3 plus 60, 2 plus 8t, like that. Differentiating each component gives us a velocity vector of 6, 8, which is not dependent on time. So it's independent of time, which implies constant velocity. So part 3, we have got to plot the points A and B and then draw the paths of the 2 boats for this time span. So let's do this up here. So there's our x-axis, there's our y-axis, there's the origin. I'm going to sketch this rather than plot this accurately due to lack of space, really. But we worked out earlier on that the point A was 3, 2. So let's say that's there. Now we know that the point B is 15, 18. So let's say that's somewhere here. Now, the paths of the 2 boats. So remember, the rosemary travels at constant velocity. Now that tells us that the rosemary's path should be a straight line between the 2 points. Like that. But let's see what else we can find out, because it would be interesting to confirm this. So the rosemary, if you think about its position, is given by this result here, 3 plus 6t, 2 plus 8t, which means its x-coordinate is given by 3 plus 6t, and its y-coordinate is given by 2 plus 8t. A pair of parametric equations. You've come across these ideas before. We're going to eliminate the parameter t and find a Cartesian equation. So let's rearrange this first equation, which gives us t is equal to x minus 3 over 6. And we'll substitute this into the equation for y, which gives us 2 plus 8 brackets x minus 3 over 6. Now I can simplify this a little bit, which gives me the final result, y is equal to 4/3 x minus 2. That's the equation of a straight line, and it tells us the path connecting A and B for the rosemary is a straight line, which again makes sense because we know it's travelling at a constant velocity. Now, what about the sage? Let's think about the sage's journey, because we're given the information for this boat as well. Now, this time we can see its x-coordinate is given by 6t plus 3, if I expand that bracket, and its y-coordinate is given by 4t squared plus 2, so expanding the brackets for the x and y components here. Now, if I rearrange this x equation here, it tells me that t is equal to x minus 3 over 6, and if I substitute that into the result for y, that gives me y is equal to 4, bracket x minus 3 over 6, all squared, plus 2. Now, I could expand that if I wanted to, but actually all that I can see here really is that it's a quadratic function, which means we're looking at some sort of parabolic curve, which means that there will be a curved movement between A and B for the sage. Now, I don't know exactly what that curve will look like without thinking a little bit more, but I know it is going to be in some sort of parabolic shape. Right, the next part of the question, what can we say about the result of the race? Well, it's a draw. The two boats end up at the same position at the very end at t equals 2, so they must be a draw. There's no overall winner. Part 5. Find the speed of the sage when t equals 2. So let's go back to the sage and let's find its velocity vector. So we know its position vector is given by 6t plus 3 and 4t squared plus 1. We used that previously. So the velocity vector of the sage, if we differentiate with respect to time its position vector, we get 6 and 8t. So find the speed when t equals 2. If t equals 2, the velocity vector of the sage is equal to 6 and 16. And the speed, we then apply Pythagoras Theorem to work out the speed. This comes to 2 root 73 kilometres per hour. So find the direction in which it is travelling, giving your answer as a compass bearing to the nearest degree. Okay, so we must sketch the velocity vector in order to find the direction of it. So from here, let's just quickly sketch what that looks like. So imagine a pair of axes like that. A vector 616 would look like this approximately. It doesn't really matter, we're just sketching. So there's the 6, there's the 16, there's the right angle triangle. Now to give us the bearing, we need this angle here, which I'll call theta, which is the same as this angle here using alternate angles. So the bearing is equal to theta, which is tan to the minus 1 of 6 over 16. So that gives us an angle of 20.556 ... So remember, it's a bearing, it's got to be 3 figures, so to the nearest degree, that is 021 degrees. So the last part of this question, find the displacement of the rosemary from the sage at time t, and hence calculate the greatest distance between the boats during the race. So let's imagine what happens during the race again and sketch this out. So here's our I direction or our X direction and our J direction or our Y direction. So here's point A and here's point B. So what we want to do is find the displacement between the boats. So let's imagine that the rosemary at a particular time is here. Let's imagine that the sage at a particular time is here. We don't know exactly where they are, but let's just imagine that. So there's the sage from our starting point. There's the rosemary from our starting point. So if we want the displacement of the rosemary from the sage, we're looking for this vector over here. So the vector SR. So what can we do? So the vector SR can be found in lots of different ways. I can work out the vector SA and then add on the vector AR, or I could say that the vector SR is equal to SO, where I take S back to O like that, plus OR, where I go up from O to R like that. Now, the original position vectors were defined in terms of the origin, so everything relative to O. So really what we're doing is using this method over here. So we know that the position vector of the sage is given by this vector over here. So we know that the vector OS is equal to 6t plus 3, 4t squared plus 2. So if I want the vector SO, I want the reverse of that, the negative of that, so that's negative 6t minus 3 and negative 4t squared minus 2. Now the vector OR is simply up here. It's the original position vector we were given for the rosemary. So let's add on 3 plus 6t, 2 plus 8t. Now let's simplify that, and interestingly you will see that there's a 0 in the I component. The j component works out to be 8t minus 4t squared. Now, what does the I component being 0 means? It means that there is 0 horizontal distance between the rosemary and the sage at any time t. So vertically, they are directly in line with each other, which actually worked out quite nicely for my sketch diagram over here, as you can see. So there's the position vector. Now, the distance between them will be the magnitude of this vector. So it will be the magnitude of the vector SR. Now, before we start applying Pythagoras Theorem and working this out, we're trying to maximise the size of this vector here, which means we want that component 8t minus 4t squared to take its maximum value. So rather than making this complex, applying Pythagoras Theorem and then trying to do some complex differentiation, let's think about this. If you want to find the greatest distance, we are basically trying to maximise this component here, 8t minus 4t squared. So we want to try and maximise that. So I'm going to call this f of t for simplicity. Now, if we want to maximise something, differentiation can help us here. So f dash t is 8 minus 8t. Now, at the maximum value, we know that f dash t equals 0, which gives us 8 minus 8t equals 0, which gives us t equals 1 second. So at 1 second, the vector SR, representing the displacement of r from S, is equal to 0, 4, which means that the maximum distance between the boats during the race is the magnitude of this vector, which is 4 kilometres. Now, the last example. In this question, the origin is a point on the ground and the directions of the unit vectors I, j and k are as follows. So they're east, north and then vertically upwards. So Alicia does a skydive on a day when there is no wind. The dive starts when she steps out of a moving helicopter. The dive ends when she lands gently on the ground. During the dive, Alicia can reduce the magnitude of her acceleration in the vertical direction by spreading her arms and increasing air resistance. During the dive, she can use a power unit strapped to her back to give herself an acceleration in a horizontal direction. Her mass, including her equipment, is 100 kilograms, and initially her position vector is this, and her velocity vector is this. So we now have a whole series of questions that we need to work through carefully. Again, you have these on the provided PDF, so you can read the questions separately as you work through them. So, part 1. Calculate Alicia's initial speed and the initial angle between her motion and the downward vertical. So part 1, her initial speed is simply going to be the magnitude of this initial velocity vector. So we want 5 squared plus 10 squared. We can ignore the 0 and the negative signs there. So that gives us root 125 or 5 root 5. And our unit is going to be in meters per second. If you want to work this out as a decimal, it's about 11.2 meters per second. So the angle between her motion and the downward velocity, again, you need to use the components from the velocity. So you can see you've got -5 and -10. So the angle theta is going to equal tan to the -1, 5 over 10, which comes to 26.56 ... or 26.6 degrees to 1 decimal place. Now, if you're not sure about why it's that calculation, just ignore that 0j component and imagine you have two other vectors, I and k. So imagine your I direction looks like that, and imagine your k direction looks like that. Now, I know you're used to that being the j direction, but it doesn't matter because you can rotate the vectors round. As long as they are mutually perpendicular to each other, you're just potentially looking at it from different angles. So if we imagine what the vector -5, 0, -10 would look like, you can't see the j direction. It doesn't matter because the j component is 0. So we're looking at -5 like that and -10 like that. So there's our 5 and there's our 10. Now the question asked us to work out the angle with the downward vertical. So where's the downward vertical? That's this. So the angle that we were actually looking for is this angle here, theta. Now, that is equivalent to this angle here, using alternate angles, and you can see from there's the right angle, that tan of theta is equal to 5, the opposite, over 10, the adjacent, which is why it's tan to the -1 of 5 over 10. So part 2, at a certain time of the dive, forces given by these three vectors are acting on Alicia. Suggest how these forces could arise. So this first force here, 0, 0, -980, that looks like a weight calculation there, m times g. Remember, the total mass was 100 kilograms, acceleration due to gravity is 9.8, so this is almost certainly as a result of her weight. Now, the second one, 0, 0, 880, is acting upwards, and that could be due to some kind of air resistance. Remember, she had her arms stretched out. It could be some sort of up thrust pushing her upwards. And then this last one has got to be due to her power pack. So that is the force from the power unit, which was referenced in the question. So part 3, we've got to find her acceleration at this time, giving your answer in vector form and show correct to 3 significant figures. The magnitude is this. So we are going back to using Newton's second law of motion. Remember, the resultant force is equal to the mass multiplied by the acceleration. So the resultant force is going to be the sum of these 3 vectors. So 0, 0, minus 980 plus 0, 0, 880 plus 50, negative 20, 0. The mass is 100 and the vector acceleration is what we are looking for. So this gives us an acceleration vector which is equal to 0.5, negative 0.2 and negative 1. Now, show that correct to 3 significant figures, the magnitude is this value here. Well, that's simple. Work out the magnitude of the acceleration. This is a little bit of Pythagoras Theorem. Again, ignoring the negative signs as they don't make any difference in the calculation. So this gives us the acceleration of 1.135 ... which is 1.14 meters per second squared to 3 significant figures. Now, one suggested model for Alicia's motion is that the forces on her are constant. Constant force implies constant acceleration, which means we can use the Suvat equations. So part 4, find expressions for her velocity and position vector at time t seconds after the start of the dive, according to the model. So we can make use of Suvat equations to do this. So part 4, let's start writing that down. So v is equal to u plus at. Let's start with the velocity. So our initial velocity was equal to -5, 0, -10. Our acceleration, 0.5, -0.2, -1, and time t. This simplifies to give us a velocity vector. Well, we can leave it like this, or we can simplify it to give us -5 plus 0.5t, -0.2t, and -10 minus t. So if we want it written as a single vector, we can indeed do that. Now, for our position vector, we're going to use the Suvat. R is equal to ut plus a half at squared plus our initial position. Remember, we were given an initial position vector in the question over here. So again, substituting in the information. So we've got -5, 0, -10t plus a half of my acceleration, 0.5, -0.2, -1t squared, plus my initial position vector, -75, 90, 750. I'm going to leave this one as it is. Now, the last part of this question asks us to verify that when t equals 30, she is at the origin. So we had a result a moment ago, which was -75 minus 5t plus 0.25t squared in the I direction. I'm going to simplify the j direction and k direction similarly. So that's 90 minus 0.1t squared. And to finish off, for the k component, I've got 750 subtract 10t subtract 0.5t squared. Now, if t equals 30, let's substitute that into this result here. So that gives us -75 minus 150 plus 225 for the I component. 90, take away 0.1 multiplied by 900. 750, take away 300, take away 0.5 multiplied by 900. And this, when you input it into your calculator, you will see comes to 0, 0, 0, which is the origin as required. Part 5. Explain why consideration of Alicia's landing velocity shows this model to be unrealistic. So, when time equals 30, she's back at the origin, so she's landed. So let's have a look at what the velocity is when she's landed. Now, we wrote down a formula for the velocity at time t, which was this. It was -5 plus 0.5t in the I component. It was -0.2t in the j component, and -10 minus t in the k component. Now, if t equals 30, and I substitute that into that result for v, I will end up with this result here, 10, -6, -40. Now, why is this model unrealistic? The vertical component of the velocity is too fast for a safe landing. So that vertical component here is -40 meters per second, and that's too fast for a safe landing. There are other calculations that we could do. For instance, if we work out the actual speed, which we can do using Pythagoras Theorem, let's work out the overall speed at which now that comes to 41.66 ... which again, that's too large a speed for a safe landing. If you like, you can convert these values into something like kilometres per hour or miles per hour in order to get a sense of how fast this is, if you can't quite see what metres per second actually is. So let's think about that. So 40 metres per second, let's convert that to kilometres per hour. So that is 40 divided by 1000 multiplied by 60 multiplied by 60. That is 144 kilometres per hour. That is far too fast a speed with which to hit the ground. It would be dangerous.